Welcome back. A simplified design of a PV system can be formed as a first step to check the viability of the design for a particular location. This type of design is aimed to quickly calculating the PV system requirements based on the customer needs and input. The learning objectives of this video lecture are to design and size your own standalone PV system. So let's get started. As the name suggests, the standalone PV system is not connected to the electricity grid as the PV system that was discussed in the previous lecture. It means that in this video we include the sizing of the storage system as well. Now let's discuss how to design a PV system. We here use a simplified design strategy that can be applied to both grid-connected and standalone PV systems. In this design strategy, only the bare minimum input requirements are known, such as the PV module type, the loads used in the PV system, the charge controller, inverter type, maximum power point tracking algorithms, and the specs of the battery. For this simplified strategy, many oversimplifications are applied. These include the use of a simplified load profile and disregarding the location's meteorological effects like ambient temperature and wind speed. Moreover, for the simplified design, we simply use the standard test conditions data of the PV modules and therefore do not take into account the sun position or PV module orientation. In this video, you are going to learn about the different steps involved in this design strategy. Let's begin. This method follows a step plan to complete a PV system. As introduced in the previous video lecture, the first step involves listing all the loads in a so-called load table to determine the daily total load demand in watt hours. A load table basically contains information about the loads that will be connected to the PV system. By filling out details such as the device type, its rated power, and its average daily operational time, the energy requirements of the loads can be calculated. As you may notice, we have used separate load tables for DC and AC devices. The total energy requirement of the respective loads are calculated by multiplying the power rating of the load with its average daily operational time. In this example, we need 1840 watt hours per day for the DC electrical energy and 2050 watt hours of the AC electricity. In this case of AC loads, there is an additional step necessary to convert the AC energy in terms of its equivalent DC energy. This is done by dividing the AC energy usage by the conversion efficiency of the inverter. In this simplified design, we assume this conversion efficiency to be a constant value of 90% for a good inverter. We need around 2550 watt hours divided by 90% is 2833 watt hours of equivalent DC electrical energy. This makes the DC electrical needs equal to 4673 watt hours per day. The final daily load demand of the system is calculated in watt hour by correcting the value for the system losses that includes cables and inverters. Here, as we're looking at a standalone system, we also have to include a rough number for the battery losses of the electricity that is stored and not directly used by the loads. Here we assume a total losses to be 15%. So now we know our load energy demand per day. It is 5497 watt hours per day. The next step is to design a PV array such that its power output can meet the load demand. This starts by obtaining the equivalent sun hours for the PV system's location. The equivalent sun hours is an important parameter when carrying out the simple design of the PV system. An equivalent sun hour, as you may recall, is defined as the number of hours per day, average over an entire year, that a certain location receives one sun illumination, and note that one sun illumination equals to 1000 watts per square meters. We can gather from this figure, for example, that a horizontally inclined panel in India receives approximately 4.5 equivalent sun hours per day. Once the number of equivalent sun hours is obtained, we can determine the total required output power of the PV system array. The output power is obtained by dividing the daily total energy requirement by the obtained equivalent sun hour value of 4.5 equivalent sun hours in this case. This gives a PV array power of 1221 watts. Now the PV system needs to be sized by determining the required total number of PV modules. Let's take the following PV modules as a reference. Nominal power output per module is 420 watt at maximum power point with a voltage at maximum power point of 31.5 volts and a current at maximum power point of 13.34 amps. To find the size of the PV array, we first determine the number of modules needed to generate the needed power. This is achieved by dividing the needed PV array power with the PV module's power at maximum power point found in the module's datasheet. The calculation shows that in this example, we need 3 PV modules to match the needed power. The question now is, how should the panels be connected? This depends on the charge controller, which is nowadays integrated together with the inverter into one component. Here you see an example of possible specs of an inverter including a charge controller. When the 3 modules would be connected in series, the maximum voltage and maximum power point is obtained and equals 3 times the maximum power point voltage of the module, in this case 3 times 31.5 volts, which is about 94.5 volts. If the modules were operating at open circuit conditions, the maximum input voltage the charge controller or the inverter would see is 3 times 38 volts, which is around 114 volts. When the 3 modules would be connected in parallel, the maximum current at maximum power point is obtained and equals 3 times the current at maximum power point of the module, which is 3 times 13.34 amps, which is 40.2 amps. In this case, if the modules were operating under short circuit conditions, the maximum input current of the charge controller and inverter would be 3 times 40 amps, which is 42 amps. So, considering the specs of the inverter and charge controller, the maximum input current is equal to 15 amps, which means that the 3 modules should be connected in series in a single string. The voltage of the 3 modules in series fits with the input range given here. Next to voltage and current, the inverter is sized based on the PV array sizes as well. So the PV power of 3 modules of 420 watts is equal to 1260 watts. The inverter should be able to handle this power. So as a safety margin, generally the inverter is rated for a maximum of 20% higher than the PV array power. In this case, the maximum power rating of the inverter turns out to be 1512 watt, which means a 2 kilowatt inverter system will do the job. Now let's move on to the battery. Let's assume an arbitrary battery that is given with the specification as shown here. The depth of discharge, or the DOD, is the depth until which the battery can be effectively used. We must now choose how the battery bank must be configured. That is, how many batteries of the given specifications should be there in the battery bank and how should they be interconnected. The minimum battery bank capacity can be derived as follows. Here we assume that the total battery bank is operating at a nominal voltage of 48 volt. Note that in the previous slide we learned that a single battery has a voltage of 24 volts. So the daily amp hours requirement is obtained by dividing the total needed 5497 watt hours a day by the nominal voltage of the battery bank of 48 volts. The daily amp hours requirement to be stored in the battery bank would be, in that case, 114.5 amp hours per day. An additional design question to be addressed is what are the number of autonomous days the battery bank would be able to deliver power? The number of autonomous days is defined as the days that the battery can supply the continuous energy load without charging the battery. It allows the system to deliver power during a period with a low solar irradiance due to cloudy days, for instance. Here we like the system to match 3 autonomous days. This means that the minimum battery bank capacity would be 3 times the 114.5 amp hours per day, resulting in 343.6 amp hours per day per cycle. As the batteries in the bank to be used have a minimum depth of discharge of 20%, only 80% of the battery capacity is used. This results in a minimum battery bank capacity for a safe operation of 429.5 amp hours. What is the capacity of a single battery expressed in amp hours? So first, given the specs, we have an energy capacity of 2250 watt hours. If we divide this by the battery voltage of 24 volts, we get a capacity of 93.75 amp hours for a single battery. How many batteries should be connected in parallel in the battery bank? This can be obtained by dividing the minimum battery bank capacity by the single battery capacity. In this example, it would mean that 5 batteries should be connected in parallel. However, a single battery has an operating voltage of only 24 volts, while the nominal system voltage of the battery bank is 48 volts. This means that 2 batteries should be connected in series. That means that the total battery bank consists of 5 strings connected in parallel, and every string has 2 batteries connected in series. The total batteries in the bank is 10 batteries. So we have seen a simple method to design a standalone PV system based on the load requirements and available system components. Note that this is definitely not the most exhaustive way to design the PV system. This method works better for places with a more or less consistent irradiance level over the year. For places with severe disparity between the summer and winter irradiances, the number of autonomous days would increase for winter and the system cost would consequently rise as well. Also, the component margins considered for the various parameters could differ from place to place based on the system requirements. Nonetheless, this method is good enough to get a basic estimate of the standalone PV system sizing. You will be able to practice more on this in the exercises of this week. In summary, we have discussed a simplified approach to design and size a standalone PV system based on the load needs, the local irradiance data, the specs of the modules, inverters and batteries. An overview of all steps is summarized in a handy table. Please note that a PDF version of all the design steps of this simplified design strategy will be made available to the students for their reference on the platform. In the next video, we will look at some inspiring photovoltaic system applications that go beyond the traditional residential and large-scale utility PV applications. So, see you in the next video.